Hi, I'm Ben-Yaakov. This presentation is entitled The Effect of PWM Converter's Duty Cycle on Conduction Losses. I'm showing here the transfer function, the voltage transfer function of basic PWM converters. We have the buck boost, and then the flyback. Now we see that they are a function of the duty cycle. Okay, the buck we have D on, V out over V in, boost is 1 over D off, etc. And then we have the flyback. This expression is for CCM, continuous current mode. Discontinuous current mode will be dealt later on. And here we have the expression. So we see that the transfer function is a function of the duty cycle. Now, sometimes the duty cycle is fixed. For example, if you have an input voltage and output voltage given, and then we like to have a certain transfer ratio of the voltages, then this sets the duty cycle. However, in some cases, we can choose or decide what is the value of the input voltage that we would like to work at, and then the duty cycle becomes a degree of freedom that we can select. Now, in the case of a transformer or a flyback with coupled inductors, we do have another degree of freedom, and that is the turns ratio. For example, here in the flyback, we have both the turn ratio and the duty cycle, and then we have to decide how to select each of them. There is another issue of limitation of the duty cycle, and that is the case of a current mode in which we know that without slope compensation, the duty cycle has to be 50% or lower, and this is to avoid the subharmonic oscillation. This is a completely different issue. It's a nonlinear effect, and this is just a limitation that I'm pointing out that one has to be aware of it. So what are the reasons for the duty cycle limitation? First of all, we have the issue of losses, and that duty cycle might affect the losses, might increase the current of the inductor and of the switching, and therefore the conduction losses will increase, as well as the switching losses, which are a function of the inductor current. And then we have the issue of inductor ripple current, which is a function of the duty cycle. And then we might have in some duty cycle high peak current, high reflected voltage for a given turns ratio of the transformer or coupled inductor. We have issues of EMI, and then subharmonic oscillation that I have mentioned. Now, in this presentation, I am dealing primarily with the effect of the duty cycle on the conduction losses of the switches. Okay, so this is one aspect. There are some other aspects that are not dealt with in this presentation. Now, basically, all PWM converters are built around which I call a switched inductor. We have an inductor, and then we have two switches. It could be two switches or a switch plus a diode, which is also a switch. And the difference between the different topology, buck boost and buck boost, is actually what is defined as input and output. In the basic configuration, we have an inductor, we have a current, and then when the inductor is connected to one switch, then this switch will carry a current, which typically say will look something like that. And then as the inductor is connected to the other switch, we're going to see the complementary part of the current, and that is that the sum of these is, of course, the inductor current. Okay, this is the inductor current. In this presentation, I'm assuming that the ripple is small, and I'm not taking it into account. This is a refinement, which I'm not going into it, because I like just to give an impression and an intuitive feeling of the basic processes regarding the losses of the switches. This is what I'm concentrating on. So in the case of a buck, the output is here at the inductor. The input is one of the switches, and the other switch is actually connected to ground. The boost, we have at the inductor, we have actually the input voltage. And then the switch is connected at one point to ground, and this will be the on time, and then to the output, which is during the T-off. And then we have the buck boost, in which the switch is connected between the input and output, while the inductor itself is connected to ground. So basically, in all these configurations, we have this switched inductor, and the difference between these topologies is really where is the input, where is the output, and where is ground. Now, the conduction losses that I'm concentrated in this presentation is due to the resistance of the switch, or if it's a diode, there'll be the voltage drop. I'm showing here like two switches with RDS on, assuming that they are the same, just for simplicity, again, just for the intuitive understanding. So the inductor is connected through this resistance to the actual load and then to the other resistance. So if we look from the point of view of the inductor, we see at any given time the RDS on, either this one or this one. So therefore, the losses due to this RDS on and the inductor current are I square RDS on. This is the total loss, conduction loss of the switches. Now, these losses are distributed between the two switches according to the duty cycle. We see it in a minute. So let's have a look at the synchronous buck. Here are the two switches, the inductor. The output is connected to the inductor, and then one of the switches is connected to the input and one to ground. So the total loss, as we have said, is I square RDS on. This is the total loss, and I'm expressing always the total loss as a function of the output current. This is something that I'm setting. I'm setting V out, I'm setting I out, or I out is dictated by the load at any given time. So these are actually given, and I'm expressing the losses as a function of this output current. So the total loss, as we have said, is the output current, which is the inductor current squared times RDS on, and then the loss is distributed between the two switches. For this switch, the upper one, we have the total loss times D. D is the fraction of the time that this switch 1 is on, and then the rest of it is the loss to the second switch, which is the total loss times 1 minus D. Very important to realize that in this case, the total loss is not a function of the duty cycle. It is a function of I out and RDS on. What this means is that for a given I out and V out, the losses are independent of the input voltage because they are independent of the duty cycle, which is affected by the input voltage. So this is very unique to the synchronous buck, or to the buck, I should say, that the losses, total losses of the switches are a function of the output current in RDS on and not on the duty cycle or V in. What happens in the case of a non-synchronous buck? Well, pretty much the same, except that the loss of this lower switch is now due to the voltage drop of the diode. Assuming a constant voltage drop during conduction V sub D, then again the power loss of the diode will be I out, again a function of I out VD times 1 minus D, and the conduction loss of the upper transistor is again RDS on times I out square D. Now the ratio between these two is given here. We see that first of all it is a function, of course, of the duty cycle. This is the distribution of the current between the upper and lower transistor, and then this ratio. So this is the voltage drop on the transistor, and this is the voltage drop on the diode. Now obviously, if the diode has a voltage drop which is higher than the voltage drop on the transistor at a given output current, then of course the losses, the conduction losses of the diode would be larger. I'm not talking here about the reverse recovery losses, which is a different story altogether. I'm talking about the conduction loss of the switches. Now, what about the synchronous boost? Here we have an entirely different story. Well, first of all, the input, of course, is coming from here. The output is coming from here. Notice that the structure, the topology, you might say, is exactly the same, except that the input now is from here, while in the buck it's the output port, and the output is here, while in the buck it's the input port. Also, we define the duty cycle as the time of switch 2, that is the lower switch rather than the upper one. This is a synchronous boost. So the structure is indeed the same. However, the inductor current now is not the output current. And since I'm expressing the loss as a function of the output current, then I have to find what is the inductor current, which turns out to be the output current divided by 1 minus D. And therefore, the total loss due to the current of the inductor, which is then distributed between the two switches, is not just as a function of I out, also a function of the duty cycle, which means that for different duty cycles, you have different losses, total losses. The distribution is again according to the duty cycle, of course, but the total loss now is not just a function of I out, but divided by 1 minus D, meaning that if the gain is high, that is, the duty cycle is high and this D is approaching 1, the losses will increase. And the reason is that for a given output current at a high duty cycle, the current of the inductor is much larger than the output due to this relationship of the duty cycle here. So the story here is really different. Similarly, the buck boost is also different from the buck. Again, the output is not from the inductor. The inductor is here connected to ground, and then the switches are connected to the input and output. The difference between the buck boost and the boost is this, that here in the buck boost we have the input voltage, while in the boost we have ground, while here in the case of the boost we have the input voltage and then we have the ground. In any case, the output is not the inductor current. Consequently, there is this translation between the output current and the inductor current. And the inductor current is again a function of the output current and the duty cycle. So we have an expression which is really very similar to the boost in terms of the total losses. The total losses now are again a function of the output current, which is clear, and the duty cycle, very similar to the boost. Now, what about the flyback? Here, we have to distinguish between two separate cases, the continuous current mode and the discontinuous current mode. Obviously, the buck boost and buck boost could operate in DCM, this discontinuous current mode. However, this is not really a mode of operation, but rather a case in which the power is going down and then you enter into DCM. On the other hand, in the flyback, the DCM is really one of the operational modes. You may prefer to work in DCM. So this is just the operational mode by itself, not just a limiting case of regular operation. So I'm going to talk first of all about the continuous current mode and then the discontinuous current mode. I'm showing here the flyback. We have the two inductors. This is a coupled inductor, the coupling between them. And then we have here the clamp, which is just for arresting the high voltage peak that will be due to the leakage inductance. This is not really part of the operation of the flyback, but rather a parasitic effect. Now for the flyback operating in continuous current mode, here are the primary and secondary current. These are the top values here. Actually, the magnetic element current reflected to the input and then to the output. I'm neglecting here again the ripple. So the ratio between these two is the turn ratio of this coupled inductor. And then the RMS value of the primary is I1 square root of D. And the average value of the current at the secondary is I2 times D. And I'm relating everything to the secondary, the output current. So taking these into account, I find that first of all, the loss of the diode is the average output voltage times the voltage drop of the diode, and the conduction loss of the switch, of the transistor, is the RMS current at the primary squared times RDS on. So the conduction losses of the switch expressed as a function of the output current this is the average current, of course, is the current squared divided by N squared D, and then RDS on. So this means that when this ratio is small, we have very large losses, or the losses will increase. So if you like to reduce the losses of the switch, then this product should be as large as possible. Now, there is another limitation to the duty cycle of the case of the flyback, and that is due to the fact that the voltage transfer ratio is a function of D times N. That is the number of turns of the coupled inductor. So if you make D small, you need to have a large N, which means that you are affecting the reflected voltage when the transistor is in the off state. When the transistor is off or disconnected, you might say, then we see at the primary the voltage of the secondary reflected through this coupled inductor, and in this ratio it will be times N, so that the total voltage on the transistor is Vin, first of all, plus this reflected voltage. So when the duty cycle is small, N must be large for the same transfer ratio of the voltages, and then you might have a problem. So this is something to take into account. And then, of course, the question of subharmonic oscillation, which I've mentioned. And again, this is an additional problem that one has to be concerned about. Now, what about the case of the DCM? Here, things are more complicated. I'm showing here a different situation here. You see that for a given frequency, the slope of the current of the primary will depend on the inductor. And then we have a dependence, of course, on the duty cycle. And then we have a dependence on the output voltage, which will determine the downslope of the secondary. So it is a more complicated situation. This is the transfer ratio, voltage transfer ratio for a DCM. We see it's a function of the duty cycle, of the output resistance, the load, inductance, and switching frequency in all cases. And this is, of course, due to the fact that the loss of a diode is due to the average current through it. The loss of the diode will be the average output current times the voltage of the diode, the average voltage of the diode. But what about the loss of the switch in this case? For this, I am now looking at it from another point of view, and that is the power transfer between input and output. Now, in the case of a DCM, energy is stored at the primary and then moved to the secondary to completion, okay? So the amount of energy stored at the primary is this amount, Li squared over 2. This is for the primary. And this is the energy times the frequency. That's the power which is actually pumped into the coupled inductor. And all this power is going out to the output, save the losses, of course, which I'm neglecting. So from this expression, I can get the peak current of the primary, from which I can get the RMS current of the primary. And therefore, the loss of the switch is this RMS square times RDS on, and plugging in the numbers, I find that the power loss of the switch is this expression, and this expression is in fact the RMS of the primary squared times RDS on. We have the power loss of the switch. Now in this expression, we see that the power loss is a function of the duty cycle, function of the power, inversely proportional to the inductance and the frequency. Kind of a complex expression here. And just to make sure that we haven't lost anything here, I'm going to check this expression by simulation. To do this, I'm first of all defining this as the RMS of the primary, because the RMS of the primary times RDS on is the loss, okay? So doing this, I can then relate these two parts of the expression, power times duty cycle over I RMS square of the primary should be equal to this term, which is the inductor and the switching frequency. So if I'm keeping the inductance and the switching frequency constant, then I should be able to run a simulation with different duty cycle and power level and measure the power and the duty cycle and the RMS current. And this ratio must be equal to a constant number for a sweep of, say, duty cycle. Okay? And this is what I'm going to do just to check this expression to see that we have not lost anything here. So to do this, I've set up a schematics of a flyback converter. We have here the coupled inductor. I'm running it with a turn ratio of 1, just for simplicity. And then I have here a transistor, MOSFET, and a rectifier, filter output, and then we have the load. The load is 100 ohm, input is 30 volt, and then the coupling coefficient is 1. Again, I like to have as smooth waveform as possible. And I'm now stepping the duty cycle. Okay, the duty cycle is stepped. This is the duty cycle here. It is stepped between 0.2 to 0.7. And I do some measurements. First of all, I'm measuring the output power. This is the output voltage times the current times D. This is this term here. And then I'm measuring the RMS of the primary. Here it is, this one here. And then I'm taking the ratio between these two, and this is the ratio between this and this. So this should be constant if the inductance of the primary and the frequency are constant. So here is the run. This is just to get an impression of the waveform. Clearly we are in the discontinuous mode. We see nicely this is the primary current and this is secondary current. These peaks are due to the capacitance of the diode, because I'm using here a real diode. It has capacitance, and as we have this transition here, we have a current through this capacitance. And then this oscillation here is the oscillation between the primary and the capacitance of the transistor. And these will corrupt actually the numerical values of, say, the RMS, so we shouldn't expect to very high accuracy in this test because of these imperfection or parasitic effect. And here are the currents of the primary and secondary during the sweep. We see that practically in all cases, up to a duty cycle of 0.7, we are in the discontinuous mode. Here are the measured results. This is the duty cycle now between 0.2 and 0.7. We see that the power going out because I'm increasing the duty cycle. RMS of the primary is increasing. And then when I take this ratio here, this ratio, and looking at it, it's about constant. It's about 7. Okay? And it should be equal to this term here from this expression, and plugging in the number. This is a 50 microhenry inductor, 100 kilohertz. I find that this ratio here is 7.5, while in the simulation it's about 7. And again, due to this parasitic effect, I think it's a pretty good match. I did another run in which I've changed the input from 30 volt to 15 volt. And again, we see the same behavior. And again, since I have not touched the inductor or the frequency, then this ratio should be about the same. And indeed, it is about the same. So what are the main points of this presentation? First of all, I've developed a expression for the RDS1 losses in the various configurations. And then I've shown that the switch losses are a function of the duty cycle when the output is at one of the switches, while in the case of the buck, when the output is out of the inductor, it is not a function of the duty cycle, and therefore the losses are not a functional or operating point. And then this will be similarly for the switching losses, because switching losses are a function of the inductor current. And if the inductor current is changing while the duty cycle is changing, then of course you'll see a change in the switching losses. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.